Hello, good afternoon. Welcome to PIKM 2012. I am Denzel from IIIT Delhi, India, and I will present my work titled iTop Interaction Based Topic Centric Community Discovery on Twitter. This work was jointly done with Ashish Sureka, Assistant Professor at IIIT Delhi, and Mayank Pundir, an undergraduate student at IIIT Delhi. Let's get started. Over the past decade, there has been a meteoric rise in the number of users who register on online social networking websites like MySpace, Facebook, and YouTube. Interactions lead to the formation of closely knit user groups or densely connected clusters of users around specific topics. We call these communities. The tendency of users to form a community structure is a significant characteristic of any social network. Community discovery or community detection in social networks has many practical applications and hence is of research interest to both physicists and computer scientists alike. Twitter is one of the most used and immensely popular social network. It is a microblog which allows registered users to share images, videos, and text in 140 character limit messages called tweets. Many businesses use Twitter as a marketing tool and implement roadmaps depending on their Twitter connections. Previous studies have also shown knowledge of topic specific communities and its key players can aid businesses to efficiently advertise and market their products. Therefore, the detection of topic centric communities can assist digital marketing teams to identify targeted consumer interest groups on Twitter. Such information could be highly valuable to plan product releases and announcement in context with the needs of the customer. Twitter is also a vibrant platform to engage and share opinions on varied topics. Twitter, like other Web 2.0 technologies, has various advantages like low publication barrier, anonymity, and ease of access. However, these advantages can be exploited by malicious users for malignant activities like cyber activism and promotion of hate speech. Previous studies show that social media is being used by malicious users for hate speech and propaganda. Hence, it has now become paramount for law enforcement agencies across the world to extract topic centric communities on Twitter around such sensitive topics and identify the key actors within these communities. However, discovering topic centric communities has many technical challenges. Twitter is a large scale social network consisting of more than 100 million registered users. The size of topic centric communities are much smaller than the size of the overall network. Thus, discovering topic centric communities in such large scale networks is equivalent to finding a needle in a haystack. Previous research in detecting communities in social media requires complete knowledge of the nodes, users in the social network. Hence, these methods may not scale to the ever increasing sizes of current social networks like Twitter. Twitter, akin to other social networks like Facebook, provides its users with multiple ways to interact with each other. Due to the presence of such multiple interactions, determining user community association is difficult. Also, a community has no quantitative definition and hence is subjective and open to interpretation. The most conservative definition of a community requires all nodes in the community to be connected to each other. However, real life social networks don't conform to such conservative definitions. Moreover, it's not possible to have a ground truth of community structures in large scale social networks. Therefore, there's a need to evaluate community structures in such networks which are devoid of ground truth. In addition, topic centric communities need to be semantically evaluated with respect to the common topic shared by the community. We try to address these technical challenges in our work. Let us look into how we address them. First up is the large scale network challenge problem. In order to find topic based communities in a social network, previous approaches require the complete network to be loaded into memory. Such methods are infeasible in large scale networks like Twitter. There is a large portion of the network which is not of interest to the topic. Also, there is a lot of waste of processing power and memory on portions of the graph which are not of interest. We therefore look into local information community detection methods which do not require the complete network to be loaded into memory. Local modularity is one such method. It was proposed by Aaron Closet in 2008. The algorithm embodies a formal mathematical proof to extract concentric communities around specified nodes within a network. The algorithm aims to maximize the structural quality of the community by optimizing a predefined objective function which calculates the density of edges of nodes within a community. The objective function is based on the structural properties of the network graph based on user interactions. Here is how the local modularity algorithm works. We first start with a seed node and initialize the community with this seed node. We then expand this seed node to obtain candidate nodes. For each of these candidate nodes, we then calculate a value based on a predefined objective function. I will soon get into the details of this objective function in the next few slides. We then select the node which maximizes this objective function. We add the node to a community. We now once again repeat this procedure until a predefined stopping condition is reached. Let us look into an example. Our initial community consists of As you can see, the procedure is iterative. We continue doing the same steps over and over again unless a predefined stopping condition is reached. Let us now look into the objective function. The objective function is called local modularity and it is based on the structural properties of the network graph which is based on user interactions. It is proportional to the ratio of the number of edges within the community to that of the number of edges outside the community. In principle, local modularity calculates the density of edges of nodes within a community. It basically rewards nodes which build a denser community structure than the ones which do not. There are two peculiar advantages of using the local modularity algorithm. First, it visits only those nodes which are potential candidates and ignores the ones which are not. Second, since it only explores the portion of the network which is of interest, it significantly saves memory and processing power. This particular property of the local modularity algorithm helps us to encounter the challenge of large scale social networks. Let us now look into addressing a second technical challenge, that is heterogeneous interactions. Twitter allows registered users to subscribe to other users' tweets using the follow feature. However, there are many users on Twitter who follow other Twitter users without interacting them. The networks formed using the interactions of users represent actual social relationships. Previous work has also shown that the actual social network of users in Twitter is hidden amidst the links. In addition, the goal of this work is to find topic-centric communities to assist agencies like digital media marketing. Such agencies would like to know the true social structure of the network. We use an existing metric called strong links provided by the InfoChimps API as a REST service. It captures the frequency of interaction between two users based on @messages or retweets. It also gives the total strength of interaction, which is directly proportional to the frequency of interaction between the users. Strong links does not reveal the way they calculate the strength of interactions. However, the goal of our work is not to formulate a new interaction based metric, but rather to use existing metrics to discover topic centric communities. The issue of heterogeneous interactions is now addressed. So we now have the local modularity algorithm to address the large scale network challenge and strong links to address the heterogeneous interactions challenge. Therefore, we can now proceed to tackle the problem of discovering interaction based topic specific community discovery on Twitter. Here is our proposed algorithm iTop. Our proposed algorithm iTop consists of 4 steps, namely warm start, expand, filter, and iterate. Let us look into each of these steps one by one. The input to our algorithm is the keyword of the topic T for which we want to discover communities. For example, we can input Apple if we want to find communities around Apple, or we can input the keyword Messi to find communities of fans of the Argentinian football player Lionel Messi. The first step of our algorithm is warm start. Each Twitter user has a small biography which contains free-form text to explain himself. We search these bios by using follower wonk, a Twitter analytics service. It is safe to assume that people who mention the keyword of this particular topic in their bio are associated with it. This step identifies a set of seed nodes for our algorithm and gives us a warm start. Here is an example of a bio of my Twitter profile. It mentions my interests like science, cricket, which is a very popular sport back in India, lucid dreaming, and movies. The next step of our algorithm is expand. We basically use the strong links API as discussed earlier to get the interactions of each seed node as we have obtained from the previous step. Each of these strong links obtained is a candidate for community discovery. The third step of our algorithm is filter. For each of the candidate strong links, we calculate the local modularity value as described earlier. We then choose the link which maximizes the local modularity and add it to our community. We iterate over these steps repeatedly until we reach the final stopping condition. The stopping condition could be something intuitive, like the number of nodes to be added into the community, that is the size of the community, or the value of R. We now describe our experimental setup. We experiment on two diverse topics, CAD, which is an acronym for Computer Aided Design, and Kashmir, which is a disputed area on the border of India and Pakistan. We search bios using follower wonk, a Twitter analytics service, to find the seed nodes for both of these topics. Instead of expanding all the strong links, we only expand the top k strong links. We choose k equal to 6, 15, 50, and 150. Previous research has shown that a person can have roughly 150 stable social relationships in the real world. famously called the Dunbar number. Studies also show that a person can have 6 close relationships, 15 general weekly relationships, and 50 monthly relationships. Recent work shows that these numbers also hold true for Twitter. This is the reason we choose these numbers. We use the value of R for the stopping condition. That is, we stop our algorithm if the value of R is consistently stable across multiple iterations. This signifies that the community would not get better in terms of structure even while adding nodes. Or the value of R is negative across multiple iterations, signifying that adding a node to the community leads to a decrease in the community structure. We now structurally evaluate the communities discovered after running our algorithm iTop. For structural evaluation, we run iTop for k equal to 6, 15, 150 and 50. The best R is computed and compared against other k runs. It must be reminded that k signifies the number of strong links. A high R value greater than zero point 0.7 suggests high structural cohesiveness, and hence R with the maximum value is the best cohesive community around the topic. The graph shows the values of local modularity R for our algorithm runs against the community size for the topic CAD. The most cohesive community is formed at 57 nodes with R equal to 0.71. The algorithm performs rather poorly for k equal to 150. This graph shows the values of local modularity R for our algorithm runs against the community size for the topic Kashmir. The most cohesive community is formed at 133 nodes with R is equal to 0.82. Just like CAD, the R performs rather poorly for k equal to 150. Following is the network visualization for the discovered community of the topic Kashmir. We compare our proposed algorithm iTop to the network degree statistic based heuristic algorithm CCD proposed by Scherchow and Langreiter 2009. On both the topics, the R values obtained using iTop are better than the benchmark CCD. The results show that CCD algorithm for both topics never improves the structural quality of the community beyond the first step. Our hypothesis is that the reliance of CCD algorithm on the follower graph of the network rather than the interaction graph leads to the formation of an incohesive structure. It also confirms that interactions on Twitter based on @messages and retweets reveal the true underlying social structure. We now semantically evaluate our discovered communities. The tag cloud shows the frequent engrams of users in our discovered community for the topic CAD. We manually inspect the frequent engrams on the CAD wiki page to check the semantic relationship between the frequent engrams tweeted by the users. For example, in the word cloud, the word PLM is an acronym for Product Lifecycle Management, a process in which CAD tools are extensively used. The word simulation occurs in the tag cloud as CAD is also used to simulate, design, and engineer before a product is released. SolidWorks is a firm which provides a 3D CAD software to design graphical prototypes. Siemens is a German company which sells PLM software. The word cloud shows that the topic based community discovered by our algorithm around care is semantically accurate. The tag cloud shows the frequent engrams in tweets of the users in our discovered community for the topic Kashmir. We manually inspect the frequent engrams in the user's tweets on the Kashmir Wikipedia page to check the semantic relationship between terms. For example, the words Pakistan, Lahore, and Karachi are found because Kashmir is a disputed region between India and Pakistan. Kashmir is also a central political topic in Pakistan, and hence the presence of words like news and Zardari. Asif Ali Zardari, who was rather the current president of Pakistan. Therefore, manual evaluations of Kashmir reveal that frequently used engrams of users are semantically related to the input topic. We now evaluate the efficiency of iTop based on user profile information on Twitter. We requested 3 independent annotators to manually go through each member in the community and check their profile information like bio, lists, and tweets. We then asked them to perform 3 checks based on the user's tweets: presence of input topic in bio, relevance of user to the input topic based on tweets, membership or subscription to topic relevant lists. In each of these 3 cases, we ask our annotators to mark either relevant or not relevant. In case of conflicts, we arranged a meeting with all the 3 annotators and discussed the issues, ironing out disagreements in the process. The table shows summary of our manual evaluation. The seed nodes were excluded in this evaluation. For both input topics, CAD and Kashmir, we observe a very small percentage of users which have the input topic in their bio. But the content posted by these users show that they are relevant to the input topic. CAD contains 84% CAD relevant users, while Kashmir contains 81% Kashmir related users. This shows that our algorithm has about 80% of precision. Moreover, 80% of the users in the CAD community are members or are subscribed to a CAD relevant list, while the Kashmir community contains 70% of users in a Kashmir relevant list. This shows that iTop is efficiently able to discover topic centric communities even if the user hasn't explicitly mentioned his interest in his profile bio. The following table shows some network statistics of our discovered communities. We see that the average clustering coefficient in both communities is relatively high. Normal networks have a clustering coefficient of about 0.3. This indicates that the community have a strongly connected structure amongst the group. A low average path length also shows that a node in the community can reach any other node in a maximum of 2 hops, thus indicating a highly cohesive group. Both networks also display a relatively high graph density. There are 2 particular limitations of iTop. First, the stopping condition parameter has to be manually encoded. Second, the communities discovered are only those who are actively connected to each other. The nodes which silently take part in the community are completely ignored and would not be considered. In this work, we introduced a new algorithm for interaction-based topic-specific community discovery on Twitter. We investigated a local information algorithm to address large-scale network challenges. In addition, we also made use of heterogeneous interactions for discovering communities. Interactions between users can help discover social structures with high precision. Local information methods can be used to address large scale network challenges. Heterogeneous interactions could also be used. Evaluation of communities across multiple dimensions, structural, semantic, and empirical, show that our approach is feasible. Thank you for attending this session. Please feel free to ask any questions over email or message me on Twitter. My details are on the current slide. I will open the floor for questions now.